Examples to illustrate the mechanics of convolution for LTI systems. So this example says, this is from your course text, Oppenheim and Schaeffer. So what it says is to consider the convolution of following two signals. So you have xt and ht. Ht is the impulse response of the system, and if you look closely at xt, well, that is basically your you can write this as ut in terms of step function ut minus u of t minus capital T, right? So that means you're considering this signal just otherwise it's zero. Okay, so the range of vision for the time that exists, I mean the range of the time for which it exists is from 0 to t. Okay, so basically it's something, it's just a pulse. Okay, so this is from 0 to t that it exists, otherwise this signal x is 0. So this is your x of t, right? X of t, and this is the time axis. Then ht can also, ht is a ramp function, okay, and it exists for basically from 0 to 2t. Okay, so if this is t, let's say, then up until twice t, this is the ramp function. Okay, so it could be something like this, and its value, if you can figure this out correctly, it's also 2t, right? So this on the vertical axis is also 2t. This is t, and this is 2t, right? Otherwise, this function is 0. That's it. Okay. So these are the two signals. These are two signals that we need to compute the convolution, to compute the output of the system. So if xt is introduced to the system, which is LTI, then the output yt is going to be given by x tau h of t minus tau. Okay. And once again, if you've seen in the past video, you have to consider the flipped and shifted version of the impulse response, ht minus tau. Okay, and the integrand is the multiplication of the two signals, that is x tau and ht minus tau. Ht minus tau is not the impulse response; it's the flipped and shifted version of the impulse response. Okay, and in general, the limits can be modified later. Okay, so let me put this minus infinity plus infinity. So for this example, now if you recall, in 2.4 we considered in past video lectures, this example 2.4 was concerning the discrete time convolution sum, and we partitioned this this example 2.4 into 4 5 intervals, right? So we do the same over here. So it is convenient to consider the evaluation of yt in separate intervals. Now in figure 2.19 we have sketched x tau and have illustrated ht minus tau in each interval of interest. So let's have a look at this figure 2.19. This figure 2.9 and 2.19 and shows x tau as an impulse which exists between 0 and t. Then you consider the flipped and shifted version of ht. So for over here, this is for negative time. This is for t less than 0. There is a shift towards left, right? Because t is less than 0, and this since this triangle pulse is existing for 2t. Okay, the difference of these 2 points is 2t again over here, right? But this is shifted towards left. So this from this depiction, the first thing you should notice that yt is 0. Okay, yt will be equal to 0 for t less than 0, because there is no overlap. There is no overlap. Okay, what overlap we are talking? We are talking of x tau ht minus tau. There is no overlap. Okay, so if you multiply x tau ht minus tau for t less than 0, well, there is no overlap. The product is 0, right? Similarly, if I look at the bottom depiction, what it shows me is that if the lower limit t minus 2t which exists, so t minus 2t is basically greater than t over here, and t is greater than 3t basically over here. So what is happening is that we are shifting this, we keep on shifting this towards right. Okay, if you shift this towards right, for example over here in this graph, t becomes a positive quantity. Over here t is a negative quantity. Okay, it's negative time. But then t is becoming more and more positive, so you see the shifts are becoming more and more towards right, right? So the shifts are more towards right for. So this is for t less than capital T. So you are in this range. So you are in this range. Therefore, you have a certain area which you can accumulate for integration. Okay, so this is a non-overlapping area which is shown over here as well. So this is again the integrand of the convolution integral x tau ht minus tau for the given range. And even if you shift this more towards right, when the t is a variable between capital T and 2t, still you have some area. You have some area to integrate over here, and this will look like a trapezium. Okay, over here you see this is a trapezium, and for 0 to t this is the non-overlapping area. Okay, so we are not interested what is beyond capital T, because up until this range 0 to t, in this range you have the non-zero overlapping area which you are interested to integrate to compute the convolution. And if your t is between 2t and 3t, even then there's a certain area left which you will of course the height is greater as compared to the previous case, it's 2t, and which you can integrate. So this is the area which is depicted. Okay, so the convolution is still non-zero, so yt is still non-zero for this range as well. But if you are going to still shift this towards, the shift is more towards right, even more towards right, where t is greater than 3t, you can see that there is no overlap. There is absolutely no overlap. Okay, so that means yt again is 0. Yt is again 0 for t greater than 3t. Okay, so for t greater than 3t and for t less than 0, well, yt is 0. So these two graphs are telling me that yt is 0 in these two regions of time. Okay, one is that the time is negative and the other is the times t is greater than 3t. Okay, so this is the variable that is because tau is your time axis. Okay, and t is a variable which is varying, right? So for t less than 0 and t greater than 3t, yt is 0 because there is no overlap. So we have to consider these three, basically these three regions of the time intervals, so that where t is as such that there is a non-zero overlap for x tau and ht minus tau. So these three regions we see, for these three graphs, we see that there is a non-zero overlap, which is shown over here as well in these three cases, right? So if you do the integration, you see this area is small compared to this area. So if I have to depict just visually from 0 to t, of course this is a triangle, and it will be 1/2 t squared. Okay, 1/2 t squared. So this is going to grow, and then again there's a trapezium, so this still grows. Okay, the area keeps on growing. It will be like this. There will be a step upwards. Okay, for 2t. Then for 3t, again you have some area which is again accumulating. But after 3t, this drops. Okay, so this drops after 3t. This has to drop after 3t basically. This, I mean, visually you can see this. I mean, this area is there, but this area is greater than this triangular area. So this is growing. But after 3t, when there is no overlap, this should drop. So yt is something like this. Yt should be something like this. But if the original values of the areas can be, well, either you use this, I mean, this is easy. You can break this into a rectangle and a triangle and find the area. Okay, add this to the previous one. So in this range for t to 2t, this will be the value of the area it has to reach. Okay, that should be the output of the system as well. And then similarly for 2t to 3t, you have to again calculate the area underneath this trapezium, and whatever is the value will be the output of the system, yt. So let's see. You see over here, yeah. So it for t greater than 3t, it has to drop. Basically, it should be like this. Anyways, this signal is the convolution. It's showing the convolution of xt convolved with ht for 2.7 example. So for these three intervals, now we are only considering this. For this, for t less than 0, we know that the output is 0. Okay, but for the other three intervals over here, you see the integration is half t squared. Okay, this is the triangle. Okay, this is half t squared. So then again, for t, which is varying from between t to capital 2T, it's a trapezium. So this is the area. Then for 2T to 3T, again you have this area. Okay, so t is a variable in all these three intervals. All right, and you see for the area starts growing for t, and then up for 2t you have more area to integrate, and then for 3t it drops down and then it is 0. Okay, so for t greater than 3t, basically your yt, the output of the system, is 0. So that's the and also for t less than 0, the output is 0, the output of the system is 0, right? So that's the again the mechanics that of the convolution that can be seen from this example. You have to consider the flipped and shifted version of the impulse response. Keep on shifting it and look out for the non-overlapping area. So in the range where it is not overlapping, the output of the system is 0. For example, t less than 0 and for t greater than 3t. But for the other three intervals, you have to do the integrations, right? And the integration is the area under the curve, that is x tau and ht minus tau, and for each of these three intervals, the area is the output of the system. Okay, so that's basically your output yt, which is given analytically as such. Okay, let's take one more example. This is again example 2.8, and it says to compute yt. So let yt denote the convolution of the following two signals. So this is again an exponential signal, and this is a decaying exponential signal because this exists for t less than 0, right? So this is going to exist for the negative time, and for negative time this will be a decaying function on the left hand side. And this ht is the unit step function, which starts at t equal to 3, right? So basically what you are looking at is ht is like this. Okay, it starts at 3. This is my ht. This is 1. Okay, and for my xt, well, it's like this. Okay, it's going to decay on the left hand side. So this is basically it's like this. It's going to decay, and this is t equal to 0. This is t equal to 0. But since we have to consider for the convolution integral, this is given as x tau ht minus tau. So again, we have to consider the flipped and time shifted version of your impulse response ht. The variable of integration is tau. So so you have to shift this. Okay, and you have to shift for certain intervals of time, see where it is overlapping. So for example, over here, you should consider the flipped version of ht minus tau. It will be something like this. Okay, it will be minus 3. This is your h minus tau, and you see that h minus tau, for whatever is t, there is a non-zero overlap. So the signals x tau, first of all, and ht minus tau are plotted as a function of tau in figure 2.22a. So we first observe from that these two signals have regions of non-zero overlap regardless of value of t. So you can see this from this figure and this figure as well. So let's have a look at this figure 2.22a. This is x tau e2 tau u minus tau, and this is the flipped and the shifted version. So regardless of whatever is the value of t over here, whether it's positive or negative, so irrespective of the value of t over here, there's a non-zero overlap. This is the area of integration. Okay, so if you multiply over here x tau ht minus tau, you have a non-zero area. So therefore the output is non-zero. But if you keep on shifting this, for example, but up until this point, you have to consider the range of t from minus infinity up until the integrand is again the variable is tau, up until t minus 3. Okay, up until t minus 3. So again t for this range, when t minus 3 is less than or equal to 0, the product x tau and t minus tau is non-zero from minus infinity to minus infinity to t minus 3, and the convolution integral becomes, if you consider this range up until t minus 3 as written over here, uh, this is the result. This is 1 over 2 e 2t minus 3. This is when t minus 3 is less than or equal to 0. Okay. Now, when t minus 3 becomes greater than or equal to 0, when it becomes greater than or equal to 0, you see what happens. There is a shift towards right in that case. Okay. So when tau is such that t minus 3, I don't need to consider tau. We can write this in terms of anyways, t minus 3, if t minus 3 becomes greater than or equal to 0, that means there's a shift towards right. There's a shift towards right. Okay, and you still have the area. You still have the non-overlapping positive and a finite non-overlapping area. So you can still do the integration and find the output. So for this region, from minus infinity to 0, if you consider this limit, the product x tau, ht minus tau is still non-zero from minus infinity to 0. So that the convolution integral is it becomes half over here. Okay, and this is the asymptotic output of yt as a limit. You see, you keep on integrating, you keep on shifting this. Okay, now this is, for example, let's call this limit at minus infinity. So this is the decaying. Input. Okay, and you will have a certain non-overlapping area like this. I mean, over here there will be a non-overlap. The overlapping area will be like this. There will be an overlapping area like this. Okay, and you integrate this, and the area under this curve is your yt. Okay, area under this curve is y of t. So basically this area is small, but as you shift this towards right, you shift this toward this area tends to grow. Okay, this area tends to grow because there will be a shift. For example, this shift, if t minus 3 is equal to 0, this the area under the curve grows. The area under the curve grows. So basically this curve is growing. This curve is growing. But then as a limit, this is going to grow up until half. This is going to grow up until half because this minus infinity, this is also both of the signals are of infinite duration, right? So for all values of t, there will be an overlapping area. There will be an overlapping area always, and since this is a decaying signal, so you can see from here e of 2 tau from minus infinity to 0. Okay, why we are considering this 0 is because this is the range of vision. This signal is this is 0. After 0, for tau greater than 0, x tau is basically 0. Okay, x tau is basically 0. Okay, so you can't go beyond 0 over here. So this the output is asymptotically equal to half. Okay, so this will be yt will be a constant value, half. Okay, so basically you will just be integrating this the exponential with the shifted version of the impulse response, and first the area grows. Okay, and then asymptotically the output, which is again the area under the curve, x tau ht minus tau, that area becomes constant. Okay, which can be seen over here. So this is half. Okay. That's all.